Hello? Hello? Can people hear me? Hopefully. Oh, someone. Okay, I think they can hear. We'll wait an extra 2 minutes. Wait. Do you guys want worksheets? Um, I can go get worksheets. Yeah. Okay. About that. Can you have worksheet of this in the rules? Here you go. Is this one sheet of paper?
Yeah, it's just one sheet. It's not that long.
So is this all the review you need from 61C?
No. Yeah, no. Okay. We'll, yeah, we'll just start. Yeah, hello. Thanks for coming to the review session. You know, there's 2 people in person, but we got 14 people online. That's good.
Three. He doesn't count?
Oh,
Is he that?
yeah, it's just that. But yeah, it is the Friday before a long weekend, so it's probably why everyone's not here. But yeah, glad to see you all here. Yeah, so I guess we'll just start. So this review session is not like comprehensive. It's not like comprehensive of like the 61C prereq. I think we have some like information on the website on what you need to know. But this is more like a review. So you should still already have taken 61C. Yeah, hopefully this will help you remember some of the stuff from that class. Yay, Evan bot.
Is Evan bot an actual bot or is it just like
Yeah, he's a
content?
I don't know.
You sure?
I like to think he's an actual bot, but I don't know.
I think we are getting real LLM bots this year. So
Oh, are we?
I don't think we have the resources for that. Budget cuts.
Okay, so yeah, so first we'll start with endianness. This is pretty important because we'll use like we'll look at stacks and like look at memory. So usually in this class we use little endian. So what that means is the least significant digit goes in the lower address. So for example, if you have an integer 0x, 0a, 0b, 0c, 0d, it goes, yeah, so it looks like it's reversed because we have the left as the lower address. So the least significant digit, which is 0d, goes in the very left. This diagram, I think this diagram is better. Usually I just look at this when I forgot which one is little endian, which one is big endian. So like we have like memory address A, and then the 0D goes in the lower address, and big endian is the opposite. Yeah. Any questions? Should be familiar to everyone, hopefully. Okay, yeah. And yeah, like I said, usually we work with little endian in this class. So some review of C. So C is statically typed. So we declare the types when we code. So all the variables have a set type. So like this is the example we give. And C is also weakly typed, and this will come later in the course, actually in like project 1. And like the first few lecture, you'll see this. This means that you can cast variables between different types. So for example, you can cast like the example here is int to size t. This means like integer is a signed type, so there can be negative numbers, and size t is unsigned integer. And yeah, as you'll see in this class, it has some security implications when you like convert types. And we have arrays, which are continuous memory of the same type. So we can have like an integer array, and these are like placed directly next to each other in the memory. So if we look at the character array, so here we have in this diagram, yeah, sometimes the diagram is weird, they keep changing. So in this diagram, like the right is lower address. So if we have an array, it goes, they're put directly next to each other in the memory. So this is the example of the character array. And pointers are address of an object in memory. So you should know this from 61C. Yeah, so pointers are essentially just unsigned integers, and so these are all memory address. So if we have a pointer that's this value FFFF4, it'll point to this location, or this location specifically. But and yeah, and in this example we have a pointer P with a value with this value, and it's an integer pointer. So this pointer, we know that this pointer points to an integer. So the computer will look at this and then go here and then treat these 4 bytes as an integer because integers are 4 bytes. So when we dereference this pointer, we'll get 8. Yeah. Does anyone have any question? Yeah.
The different types of pointers have different sizes.
Yes. Great question. So the pointer has so in this case, P is the pointer, right?
Yeah.
And pointers always have the same size. So in this case, it's 4 bytes.
All pointers.
In a 32-bit system, all pointers are 32 bits, and in a 64-bit system, all pointers are 8 bytes, because 8 bytes make 64-bit. And in this class, we usually work with 32 bits system. So you can usually assume that pointers are 4 bytes long.
So an int pointer and a car pointer both have 4 bytes.
Yes.
Correct.
The difference is that because a character is a single byte, if this is a character pointer, it'll go here and then only look at this single byte because a character is a single byte. But the pointer itself takes up 4 bytes because it's the location of the memory.
What if it's a void?
That's the void pointer. That just means there's no type. And I think when you like the type, the only reason we put a type is when you dereference it. The program needs to know what type of the data is stored at that location. So the type determines the type that's stored at that location, if that makes sense. Hopefully that makes sense.
Because you want to read it, that's why.
Yes. So usually we don't dereference a void pointer. Yeah. Okay, we'll keep going then. If you wanna talk about this part.
So hexadecimal is a different numerical system, and it basically represents numbers using a base of 16. So on the right, here are some examples of different numbers in hex, like 0x01 is 1 unsigned. The numerals 0 to 9 are the same as in decimal, but we also have the numbers 10 to 15, which are represented using the letters A to F. So some of the pros of why we use hex is it's more readable than binary, and we can easily convert it to and from binary. So here is an example of how we would convert a number from hex to decimal. So each of the places can directly be converted to a decimal value by multiplying it with 16 to the power of the place in the hex number. So like for example, if we have a 4 as the least significant digit, we can just do 4 times 16 to the 0 to get 4. Okay, so the number system that we usually use for signed numbers is 2's complement. So it's a way of representing negative and positive integers using n number of bits. So the smallest number is 0b1 with all zeros, and it represents negative 2 to the n minus 1. And the largest number is 0b0 and then all ones, which represents positive 2 to the n minus 1, and then subtract 1. So some general properties of 2's complement are it's easy to do math with. Each bit sequence is a unique number, and most commonly, it's the most common way to represent signed integers. So usually the way we convert from 2's complement to a signed decimal number is if the leftmost bit is a 0, that means it's a positive number. So we just do the normal conversion from binary to decimal. If the leftmost bit is a 1, that means it's a negative number. So we flip the bits and then add 1, and then we can convert to decimal, and that will give us the original number, but positive. So we just add a negative sign to get the original negative number. And then for the other way around, for converting from signed decimal to 2's complement, if the number is positive, we can just convert normally to binary. If it's negative, then we convert it as if it's a positive number, and then we flip the bits and add 1. So hopefully this is all review from 61C. Okay, so now we're gonna start working on the worksheet questions.
Yeah.
So we'll give you guys some time to work on the question.
Yeah, we can do the first question. Does anyone have any question about hex or 2's complement? You can put it in the chats for people online. We can do 1 to 3 first. 1.1 to 1.3. Oops. Yeah. No, I think we can go over. Okay, so the first question, what is the hexa decimal value of the decimal number 18? Did you get that?
0 x 1 2.
Yes, that is correct. Yeah, so the way you do this is, so we know the well, for a small number it's easier because we can look at wait, let's go to this slide. Yeah, so the least significant digit represents 1 and the second least significant digit is 16. So for this, so we look 18, we know that it's 2 digits because it's greater than 16, and the first digit it's obviously a 1 and the second digit is a 2 and that adds to 18. Did that make sense? Hopefully this easy, but if you don't understand, you can ask in the chat. But we'll just move on to question 2, which might be harder. You might be tempted to convert this to decimal, but that's a bad idea because the numbers are too large. But to do addition, we can do the same thing with how you add decimal numbers. So we can add each number and then carry the digit over. So if we look at this example, actually, did you guys get this one? No? Oh, do you want to talk about your solution? How did you do it?
It's got the same number except like hex 8333988 and then but 53.
Oh, yes, that's correct. Yes.
That's it.
Yes.
You just gotta be careful that it's base 15, so every 15 numbers goes up. Is that it?
Yes, so if it goes over 15, you like carry like how you do decimal addition. Did that make sense? Yeah. And the next, yeah, so this example we will carry. So do you wanna, oh hi, are you here for the review session? Okay, yeah, you can take a worksheet.
I'll take a worksheet from there once I'm coming over.
Yeah. So do you wanna try doing this one in your head quickly?
So it's gonna be 1F, right? 16. And then I'm trying to guess them. I'm figuring 16 into hex. It's not 1F.
What's 16 in hex?
My bad.
So
It's 1 0.
yes, it's 10 because if you have 1 at the 16th place, like the first digit, like the second least significant digit will get 16. So how do you add them?
So you just add them like 2 and then 1 plus F would be 0. Then you carry the 1. 1 plus D would be E. So it would be 5550 ECE02.
E02, yes, perfect. Is it what you got this?
555 E C E 02, yeah.
Yes, exactly, yes. Okay. So we can do let's just do 1.4, I guess. And see how people do.
It's supposed to go till 7, right?
Yes, we have plenty of time and not a lot of people, so let me know if you have any questions.
Okay. Is this the first discussion?
No, technically, this is like discussion 0, so it's not a real discussion.
Okay,
So next week we'll have like actual discussion.
discussion 1.
Yes, and there'll be like 4 times. So you can go to whatever discussion.
Are you teaching a discussion?
I think, yeah, I will be teaching a discussion.
But you don't know if you're teaching a discussion?
No, I will be, sorry.
I am taking 61C at the moment, but I took some of it and I know C.
Okay,
So I
then,
hope I'll be okay.
yes, you should be good.
Yeah,
But, you
I
might
have
need
C,
to,
yeah.
you might need to like watch some lecture. 'Cause
Yeah,
we don't recommend it, but I also took it
in the
Like-
same semester.
along with 61C.
Yeah,
Yeah, I also took them in the same semester.
yeah, it's like when David Wagner's teaching it, why not?
He's a really good instructor.
Yeah, he is.
Yeah. He's-
What is decimal? Sorry, I just came right now. So decimal means this is 1610, right?
Yes, yes.
Okay, sounds good.
Also, you wanna go over?
Are you ready to go over this question?
Yes.
Okay. So first I asked, what is the largest unsigned 32-bit integer? So since it's unsigned, that would just be 32 bits of all ones. So in hex, that would just be 0x and then 8 f's. But then it asks, like, what is the result of adding 1 to that number? So since we're still using 32 bits, but we're adding 1 when all the bits are already 1s, then they'll end up carrying over. And then it would be like, you would need to have like a 1 in like the 33rd bit spot, but because we only have 32 bits, it just becomes all zeros.
Overflow.
Yeah.
Yes.
Okay.
So the next question is kind of similar, but it asks about signed numbers though.
Can keep going.
Hmm?
You keep
Do we need time to work on this?
I've done it, so.
Signed turn to the. So. Okay, I think I need 1 minute.
Alright, yeah, take your time.
Like, you guys hate your lives. The energy level is so low. You guys are being forced to do this.
No.
Don't be here at all.
No, okay, maybe I should use one.
Just one of
I'm
them.
very excited.
They're depressed that there's so few people.
Yeah, that is true.
I think
But
they're impressed that they're Berkeley students, I think that's a more.
That is
No.
very true, they're depressed because of that.
no, I'm not. Maybe
You're
you.
depressed of being in Berkeley.
Guys, if you're depressed, we have student support meeting.
You are.
Yes. Make sure you reach out. Or you could also reach out to our school's mental health service.
Honestly, I might need to do that at this point.
Yeah, but
Wait,
this class is pretty generous.
What?
There to help you.
I had a question. So sine is. So is there always one more? So there is zero. There's a set of positive numbers. Oh shoot.
Wait, is this all the review is?
Yes, this is the whole review. So
Yeah,
you,
I thought we were gonna go over like, I don't know, memory management.
no.
You don't need that, right?
Wait,
Uh,
there's like a few slides about it at the end.
Like pointers,
Oh,
like when pointers get messy.
We have like a few slides, but it's not that. Like this is pretty basic. Oh well, I don't want to say that. But this is like more of like a rough review for the stuff that we'll use in the first part of the course.
I was just thinking.
So
for-
yeah, we don't know that. Yeah, oh,
For the sign, like representation, is there always one more of a positive number than negative number? Or like, how does it work? I forgot. One more, because there's
Wait.
zero, and then there's negative numbers and positive numbers, so excluding zero from the positive. So is there one more for the positive than negative, or is there one more of the negative than the positive?
I think it's one more than negative.
yeah, that's a good question. Yes, there's one more for it.
Like, if you have, say, like,
Yes, you're right.
-8 to 7, right? I'm just saying.
Yes,
Okay,
you're
okay.
correct. So if it's that's like how many bits is that? 4 bit. Then it's -8 to 7. Yes, good point. So yeah, that's why I have the slides.
You can go back to, oh shoot, it does say there.
No,
Sorry, my bad.
no, it's all good. I had to I had to think about it too.
2 and minus 1.
One more negative number, right?
Huh?
Yeah, one more negative number than positive numbers.
Yeah,
Yeah,
so. 2 to the power of 31.
the infinities. So there's only 2 people.
Huh? There's 3.
3, sorry.
Well, there's like 15 people online. Everyone's home for break, man.
Yeah, because like you printed like so many of these.
Yeah,
That's what I'm saying. Like,
That's true.
like, I don't know, like
Bro,
I can see it over here, right here.
That's
I mean, you
true.
can take it home if you want.
No, I just came from 61A stuff. Wow, there's so many people there.
Oh, I think this room had like 61B.
Oh, a meeting, right?
Yeah,
Yeah,
it's quite. They have big staffs.
then you kick them out.
But yeah, we should continue.
Are you guys ready to go over this one?
No, I think we need 2 more minutes. I'll start it.
That's fine. We have so much time.
Oh, you're done. I'm not done. Okay, fine. You can go. Go. You can go.
Okay, but we do have 2 hours though.
Yeah, we still have plenty of time if you want.
Okay, great.
But
I feel really bad that you guys are
Okay.
standing. You guys should sit down.
no, it's Didn't say anything. Okay, I think we can like work on this. Okay, so did you get the first part? you got this? Do you wanna explain your answer? No.
Math is social.
Oh my god.
Man. Okay, so I think a good way to start is like think about it in binary. So what's the largest signed 32-bit integer in binary?
It should be 2 to the power 31 minus 1.
No, the actual number doesn't matter, like.
In binary, I just don't know how to do it in binary size.
Okay, it's so how do you know it's 2 to the 31 minus 1?
Because that's what it said on the slide.
Oh,
Okay,
Okay, I get it.
It's 1 minus, yeah, I think he has something to say.
if you want to make the biggest, largest number possible,
Yeah,
and you have 32 bits, right? How can you make the biggest, largest number possible?
okay, so that's unsigned, you make all ones. You
Yes.
make all
Yeah.
all bits 1.
Yeah, okay, so now if that number is supposedly going to be signed, what is the difference between signed and unsigned?
Bruh.
Okay, so
I studied this, I forgot.
if we're doing unsigned numbers, the leftmost bit is your sign, so.
Oh, okay, so
you're
positive
left-
is 0 and negative and is 1. Okay, left.
yes.
Yeah, okay,
So-
great, so it's gonna be 0, yeah, 0, 1, 1, 1, 1, 1, yeah.
Yeah, which if you translate it to hex is gonna be that number that it's gonna put up right now.
Yes. Did that make sense? Okay, I'll explain again for the people online or for the people watching the recording. This recording is going to be kind of painful to watch. But too bad. Should have came in person.
Wait, the recording's not happening?
I'm sorry. Huh?
The recording's not happening?
No, the like we're recording the Zoom. We're on Zoom. There's like 9 people on Zoom.
Used to be 14.
Oh.
Yeah. Okay, yeah, don't uh so yeah, so what we talked about is that the largest signed 32-bit integer is basically you have the first bit at 0 because the first bit like indicates the sign. And obviously we want it to be a positive number for it to be the largest, and the rest of the bits will be 1. And if you convert that to hex, it will be 0x7 and then 7f. Yeah, and then if we add 1 to that number, should be
It should be the smallest number. So 1, 0, 0, 0, 0, 0.
Think about it in terms of bits.
Yeah, so the leftmost is 1,
Uh-huh.
and then everything else is 0,
so
right?
no, we add 1
The
to the
left one is, the leftmost is 0,
so you add 1 to this number.
because it's positive.
But isn't this the largest signed 32-bit integer? So if we add a 1 to this, then it's gonna go from the largest one to the smallest signed 32-bit integer.
Oh yes, I think you got it, but 1000 and that's in
Yeah,
I think you're
11000
in binary, right?
isn't the smallest.
No, wait, in
Because
binary, you mean,
111
wait, are you saying in binary?
Yeah, in binary, I thought 1000 is the smallest representation.
That is wait, is that?
That's what I caught.
Yeah, that is the smallest. She is correct.
Yeah,
So yeah. So if you, so yeah, that works. Or you can also just look at this and add.
wait, so it's gonna be
Yes,
A0.
yes. Yes,
Wait, 10000 isn't the smallest.
it is the
It
smallest.
is in binary, but
Yeah,
in
it-
hex, it's 8.
Yeah, I'm talking about binary, because 111111111 would be the smallest.
That's -1. If you have all 1, that's actually -1.
Just like
Oh yes, hex is very convenient.
in cybersecurity.
In like a lot of fields. In like of
Binary instead of.
oh right, because hex is shorter. That's literally the whole reason.
Oh, are we gonna be working with hex? like
Yeah,
that?
hex is
Yeah.
more readable and
Okay,
it's easily converted. Yeah, so good question. It's just because it's more readable. It's shorter. Yeah, or else we'll be writing too much once. Okay, let's go back. Getting off track. No, you're good. It's a good question. But yeah, so if we add 1, we keep carrying the digit, and it'll become 0x this number, and then 7 zeros, yes. And then we were discussing like what is this number in 2's complement, and it's actually the smallest.
Because you're flipping the bits and you're adding one.
Yes,
right?
exactly, yes. Because if you convert it, you'll understand. Yeah.
Okay, great. Wait, what is 2?
Okay, this is a reading comprehension problem. I don't like this problem. I remember this one.
I took reading 4 years ago. Reading.
Okay.
Wait, what is 2's can we just go back to 2's complement one time?
Sure,
Just
sure,
keep
sure.
slide for 1 second. I'll do that.
Sure.
I'm sorry.
No, you're good. So what's the question?
Okay, I got it. Okay, sounds good.
Okay, so
The negative numbers would be. If you interpret, okay, unsigned. Rather all unsigned, okay. 1 0 0 0 is negative. And unsigned. 1 2 3.
okay, so I think I'm just gonna explain this question because I have to read it 3 times to understand it. So basically what this question is saying is that let's imagine you have like a positive number and then a negative number, and then both of them are in 2 complements, right?
Yeah.
But then you like you just cast it to a signed number. Yeah, unsigned, sorry.
Or are you treating the binary representation as unsigned?
That's the same thing. That's basically the same thing. What casting means is basically you treat the like the data, the underlying data as another type.
Like if your negative number is say 1 0 0 0 0 0 0, so now we're just treating it
Yes,
as
yes.
as say, yeah,
Unsigned, yes. Yes, you're right.
Would the negative numbers be smaller? They would be larger.
Yes, exactly. Okay, looks like everyone got it. Yeah, so because if we have like a negative number, the first digit is 1, and the first digit in binary is 1, so it'll be larger.
Do you want me to go back to something?
Sure.
I don't know why working with binaries gives me a break.
Yeah, blah 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 blah. Yeah. So another way to do this is you can just pick a negative number, like -1, and then +1, and then -1 is basically all ones in binary. And if you look at that as a unsigned number, that's like a very large number. If that makes sense. Okay. Okay, no one's asking question online, so we'll just keep going.
Car 16.
Yes.
16.
So car.
Car has one byte represents each car, and this is an array, so you need 16 bytes.
Yes. Exactly.
Is this a trick question?
No, it's not a trick
You
question.
need 17 because it's 0,
Yes.
1 2 3 4 5 6 7 8 9 10 11.
So good point,
17?
but we don't because
No.
basically we have this character. This is basically 16 bytes, but you point out that we need like the null terminator, right?
Yeah.
So this is still 16 bytes, but we can only put a string of
15 characters.
yes, exactly, because we need the null terminator.
So so you can put 15
Characters, yes.
Yeah.
Yes.
from 0 to 15, and the 16th one would be
A
null
null
terminator.
terminator. Yes.
It's always set to the null terminator when we instantiate a character array in C.
It's not.
So we need to individually do it.
Yes.
if
but-
you, if I know if you equal it to a string, if you have
Yes.
a variable and equal it to a string, that will have a null pointer. but
Yes.
not when you
Yeah.
Yes.
But when you just do say char bracket 16, then it does not.
Yes.
Okay.
It does not initialize it to anything. Yep.
Yeah, so we don't need to even worry about null terminator.
But yeah, that's a good point.
Right.
Yep, 16 bytes. Blah blah blah. Yeah, each character requires 1 byte. Okay, this one we can also just talk about it.
Isn't an integer 4 bytes?
Yes.
So 4 times 8 is 32 bytes.
Yes, exactly. 32. Nice.
I think the text is a bit wrong.
No, that's an int though.
Yeah,
You
each
just need
integer. Yeah,
character.
you're right.
Oopsie. Is no one taking this class along in 61C?
Usually
they don't.
there will be some because it's a large class.
Is it only 9 people?
No, the class has like 200 people in it.
Oh, you mean
Wait,
if
why
there's
so few people?
um
It's a Friday at 5 p.m.
yeah, because it's a Friday.
Before a
uh,
long weekend.
They don't want to hear me ramble about 61C.
It's okay, I wanna.
Oh, I'm
I wanna
Connor.
hear you ramble about it.
Yeah.
Jocelyn.
Jocelyn.
I'll always be here if you wanna ramble. Not just about 61C.
Um,
Well, what if we don't want to get a thought?
yeah, you weren't here when we went over it, but we can go back at the end.
Is everyone okay with that?
Yeah, sure.
Thank
I
you.
mean, I'm just
No,
like,
I'm
I'm
saying
just like answering emails right now, so you can chill.
I'm saying we'll go over it first and then we'll go back. 1.7 was 16.
But yeah, we did. this.
Now someone's asking on the chat.
Oh, what was the question?
What's the answer to 1.7?
Oh, okay.
Chat, is this right?
Yeah, so 70 is wrong because basically character array is 16. So it's 16, and we can only put 15 characters. So there's no, it doesn't add more space for the null terminator.
Yeah.
Okay, we're gonna go over this so the recording is at least a little bit bearable to watch.
Watch it on times 4.
Are we gonna get this by 6 o'clock?
Yes, we're gonna end by 6. This does not take,
2 hours.
yeah,
Not take. I don't know why you guys
this does
said
not take 2 hours.
100%. Like,
I was, bro, I brought this. I was reading this before this.
Okay, I can, there's actually,
I was reading this. I was so ready for that.
Oh, you were
I was like,
so
"Oh,
ready."
shit, it's gonna be tough.
yeah, it's not.
you already.
Okay, so
Okay, wait.
do we get this? Okay, let's go from.
Wait, what is little? So
So
it's
this is the
mo-
lower address.
It's the most significant byte stored at the smallest address or the largest?
Higher, is that higher address?
Okay.
Okay, so yeah, so we'll just do this real quick.
It's gonna be EFBEAD.
Yes. So here we have the lowest. So here you put EF because that's the lowest address. And you put the least significant byte.
So wait, yeah.
And then B, and then so we all got that, right?
Wait, most significant. It's a DE.
Are you guys juniors or seniors or?
Junior. Are you?
That's my last semester.
Okay. Two.
I'm a senior.
Senior.
So on the discussion page, is the last box the highest address?
Yeah, it goes left lowest,
Okay,
left, right highest.
Okay.
This block is the highest address.
it just
On the
doesn't
worksheet, there's
say-
only one row.
Oh, it says it here, but yes, it's kind of.
Oh,
Does it not say?
And it doesn't-
Oh, it's different. Oh, okay, guys, it's different from the worksheet.
That's.
I think it was different the last time too. They just didn't fix it. Sorry about that.
So it should be sorry, okay, yeah, great.
Yes. Yeah. So okay, we need to go faster so the recording is bearable.
It is gonna be bearable. It's like, we could finish this in 5 minutes.
Yes. So
Like,
yeah.
literally.
Yeah. So
Pretty sure.
okay, if you have a question, okay, if they have a question, they can just ask on it. But I know who will watch the recording. I'm sorry. No, I said I don't know who will want to watch the recording. Okay, thanks. Why not?
Maybe they will, but they will like be like, okay, fast.
They're like dissing you already.
It's just, I don't think no one will want to see a 1-hour lecture.
That is true, and there's like 2 topics.
They're like, what the hell is taking them so long?
What's the difference between 32-bit and 64-bit system?
Oh, yes, we talked about this. Watch the recording. Um. Oh, sorry. Yes, we need to stop, guys. The people online are complaining.
Okay,
Uh,
so I'm thinking it should be D on the right, E, A, D, B. Okay, so it should be F, E, E, B, D, A, E, D.
Wait, what?
I said F, E, E, B, D, A, E, D. Was I right or wrong? Like dead beef, basically opposite direction.
In the little.
It'll still be byte by
But
byte.
but there are 8 boxes.
Yeah. So there's actually, you just fill in the rest with 0
Oh,
because it needs to fill up 64 bits.
Yes.
sorry. I was like,
Okay, this is a trick question. Basically,
it is a trick question.
because it's 64-bit and address takes up 4 bytes. So the pointer is actually 0x and then 8 zeros and then dead beef. But we don't write down leading zeros. But inside the memory, it'll have leading zeros. Yeah.
Okay, sounds good.
Yeah, so you should be writing this row first and then this row. Yeah. Okay, the last question. Yes, pointers will require 8 bytes.
How do you represent the character array A, B, C, D, E, F, G, H?
The bottom row come first. Someone's asking. So you would write E, F, B, A, D, D, E, and then zeros. Maybe we should edit the slides.
Wait, can we go to the next?
It does say on the slide left to right and bottom to top.
Yes.
So is the bottom left the lowest? Then what's the second lowest? The one
This
above
one,
of
this one.
the-
No, this one.
The okay, great.
Okay, how would we build a character array? So we just put the characters in order.
Each block is 1 byte.
Exactly, yes. Yep.
You showed the answer.
Yeah, because okay.
Okay, yo, now we know the answer.
She's just gaslighting him.
No, I already told you. You just put them in order.
No, but the way. Wait, never mind.
Okay, yeah. So yeah, can we go over
There's no. Wait, go over what?
this question now?
Yeah, yeah.
Were you gonna ask something?
Thank you for being so considerate. I was not.
So yeah, we just
Joking, sorry.
we just put it in order. Yeah. Yeah. So the first character goes in the lowest address and then so on. Yeah, this is not a trick question. Yeah. For arrays, first element will always be at the lowest memory.
There is no concept of MSB or anything here, since all of them are just taking 1 byte.
Yes, exactly, yes.
But if you had an integer array, then like, it would be,
Yes, so if you have an integer array, it's a good question. If you have an integer array, the lowest 4 bytes will be the first integer in like the little endian order. Yep. Okay.
Is each block 1 byte typically?
Yes, typically, yes.
yeah.
Or was it 2
Uh,
bytes?
No, each block is 1 byte.
Always?
No, but it depends on like, this is just like
It's a
drawing.
32-bit system.
Yeah.
So in a 32-bit system, each block is always 1 byte.
I mean, in the paper it is. Also, if you look at question 9,
For this worksheet, it is. But yeah, it depends on what do you like, how do you draw boxes?
what do you have block of memory?
I think you're asking like just the box on the worksheet, right?
Yeah, but like also like,
In general?
yeah, because you know how in 61C we used to have like this space, which was a square, and like you had the addresses on the top. So
Yeah, so
yeah, each byte was.
so you'll see later, later we'll practice like stack diagram. And then in that we have like rows of memories, and then each row is 4 bytes. But so yeah, so it depends on like the context. But on this worksheet, only each box is 1 byte.
Each page was 1,000 bytes.
That's 61C.
What is a page?
So that's not we don't use pages in this course.
Okay.
But yeah, so if you need like review about pages, you should go watch 61C lecture. But we don't need that for this course. Yeah. Yeah, so this is for reference. Did you guys use GDB in 61C?
Yeah.
Long time ago.
Oh yeah, so
Can you VS Code? Just wondering.
yes, you can use VS
It's,
Code.
I just find, like, can we do, like, instead of Vim, can we do VS Code with GDP? There's-
I'll answer that later. Let's finish the review session first.
There's no restriction.
In 161.
We can chat about that later.
Yeah.
But yeah, so this page is like all the GDB commands. So in project 1, there's a walkthrough video. But yeah, if you need reference, you can come back. And yeah, this is also a review of GDB. You can just look at this for project 1. You want to talk about this? I think we're good.
We'll go over it more in like lectures and like project.
Yes.
Are the first couple of discussions going to be like on Slack and stuff and like more in-depth C?
Yeah, like there would be x86 review and like memory stuff.
But we didn't have a.
Yeah, it's not review. We just go over x86.
Before risk 5, right? Everything before risk 5 and 61C is in 161.
No, we don't use everything, but we have it on the website. You can check the website.
Okay.
But yeah, we can talk about printf a little bit.
What is N? %n.
Sure, we can talk about it because you'll look at it again when you do the project. But this is not in 61C, I think, right?
No, I haven't seen that either.
Okay, sure. I'll talk about printf first. So yeah, so the way printf works is you have the string as the first argument, and then you have percent signs with a specifier, and that will be additional arguments. And then here the %d will be replaced by the value of num, and then %d is a signed integer, so it gets placed here. It gets placed here. The value of num will be printed out at the location of %d. And the % is a string, so the value of word will get placed here. And yeah, %n is the new one. Yeah. So what %n does is it'll like the argument will be a pointer. So there'll be a pointer at the end, like as the argument at the location of %n, and then it'll it does not like print anything. It'll just look at how many characters are printed out at the location of %n, and then it'll write that value to the pointer. And if that doesn't make any sense, that's okay, because you'll run into this again, and I'm pretty sure we'll explain it, because it's not in 61C. I think it's in lecture when we use printf. But yeah, that's all. I'm sorry to everyone online or watching recording that we keep getting sidetracked. I am very sorry. Well, yeah. No. Okay, yeah, maybe. Okay, but I also got distracted, so it's also kind of my fault. But yeah, thanks everyone. Yeah. You're welcome. Yeah, sorry for the interruptions.
They were all class specific, it's fine. It's okay.
It's all class specific. And I'm sorry for the interruptions.
Okay, now we can chat, guys.
Wait, and
Or
the-
huh?
and the recording.
I think it's fine. It's
Can you check?
wait, someone's talking. Is there a review session? Yeah, there is review session until 7, but this is all we have, so the rest of the time is questions. So if people have questions online,
Did you end the recording?
no, not yet.
Right, you should end it.
Should we though?
Should see if you have.
You know, we could,
questions, but
you know,
if they
there's-
don't,
I know why, but there's like more slides.
It's just that I feel like our questions are going.
This is
to
like-
red on this recording. This one.
Do you want to go over x86?
Sure. I mean, I would like to. If people would. answer.
Everyone left already. This is for those who stayed.
Are we the only three?
There's one person online.
Dude.
There's one person on Zoom. But yeah, everyone you can leave now. This is like preview. I think this is because the course is used to ran differently. I think maybe 61C used to have x86 or something.
No.
Yeah, I'm not sure.
These ones never had.
It never had?
x86.
Yeah, I don't know.
There was
So
only-
this is new, x86 is new.
It's the same, so x86 and RISC-V.
You can-
both
you can leave if you want.
ISAs. ISA means in structure set
Yeah,
architecture,
yeah,
right?
yeah.
RISC-V was developed by Berkeley.
Yeah.
That's where they teach it. here.
Yeah.
x86
we're-
is the standard for
Yes.
Intel chips.
So we do RISC-V, but do we do x86 and 61C? No.
Yes, a little bit towards the end,
Okay.
just a tiny bit.
Okay.
Oh yeah. Yeah, we're just doing questions now.
Are we gonna cover x86 in depth or
No, but we also
know x86 from 61C.
no, you're not. We they don't teach x86 and 61C.
Okay.
So we'll cover that. Right. I'm pretty sure that's how it works.
Okay. Can we see the next slide?
Sure. I mean, this is on the website. The slides are on the website.
I mean, we
They're
were
not on
questions, so that's why I thought.
Yeah, the slides are on the website, guys.
Calling. Oh shoot. Okay.
Yeah, so this is for after you go to the lecture, you can look at these. We can do some preview. That's for fun. Okay, let's end the recording. I don't want this to go in the recording. Okay, maybe I might ask the TA to like share a previous year recording. Okay,
We're just
bye.
end the recording. Wait, so everyone is kicked from Zoom?
Oh wait, someone asked a question. Oh, I'm so sorry. Should the answer be HGFEDCBA? No, because oh, this is so bad. Someone asked a question. Because arrays goes in from lower address to higher address. Arrays doesn't. What was I gonna say? Okay, I'll just type it later. But yeah, so the student's asking should an answer of 1.11 be HGFE?
HGFE.
And then so on and so forth. So like in reverse. No, because like arrays goes from lower address to higher address, and little endian and big endian doesn't affect this in this case.
It's 1 byte per box. So. Right.
Yeah.
Like, how do we know for a system?
Yeah, bye. Sorry about that.
Oh, sorry.
I'll end the meeting.